All right, so we're going to talk a little bit more about applications of the normal distribution. Consider the IQ scores for people. IQs are normally distributed with a mean of 100 and a standard deviation of 15. If a person is chosen at random, what's the probability that his or her IQ is between 100 and 115? That is, what is the probability that X is between 100 and 115? Well, if you continue to do it the way we've been doing it, you would have to find a z-score for 100. So we'd go and we'd find 100 minus 100 divided by the standard deviation, which would give us a z-score of 0. And then you could go and find the z-score for 115. Divide by the standard deviation, and we get z is equal to 1. So we'd be looking for the probability of z greater than 0 but less than 1. And we think back to the empirical curve, or the empirical rule, between negative 1 and positive 1, 68% of our data lies. We don't even need a calculator for this problem, so half of that would be 34%. There is another way to do this. When we convert a score into a z-score, that's called standard score, or standardizing the score. We can also use a calculator to find probability without standardizing the score. You know, when we put this in a calculator, we do normal, CDF, lower boundary would be 0, upper boundary would be 1, mean is 0, and standard deviation is 1. And if you do that, you're going to get something around 0.34. I'm not going to do it, so I'm not sure exactly what number you'll get, but it'll be roughly 0.34. If I want to do this without standardizing the score, and I have that capability with a calculator, let me erase all of this. I can do that by selecting normal CDF again. And this time I'm going to put in a lower boundary of 100, an upper boundary of 115, and the mean with of the data is 100. And I know that 15 is one standard deviation. So the syntax is the same, except it's not standard scores. So it's still lower bound, upper bound, mean, and standard deviation. So that'll save you some steps. And when I do that with my calculator, I get 0.3413. Pretty close to 34%. Okay, so let's erase some of this and do the last part of the problem. Actually, let's erase all of it. All right, find the probability that a person selected at random will have an IQ greater than 90. So draw yourself a curve to demonstrate, or to keep track of what you're looking for. I know that the mean is 100, that comes from up here. I know that standard deviation is 15, so 90 is less than 100. and I'm looking for greater than, so that's to the right. That's going to help you set this up. So I'm going to put this data in without standardizing it. I'm going to choose normal CDF. So lower bound is the number furthest to the left. That would be 90. And then you'll notice that I'm looking for everything greater than that. That means, and that since this curve extends indefinitely, that is going to be infinity. So you'll need to put infinity in your calculator. And then the mean, we're looking for the mean, that's 100. Not the standard mean, but the mean of your data. And then standard deviation is 15. It has not been standardized yet. And when I calculate that, I get 0.7475. All right, here's one for you to try. The transmission on a model of specific car has a warranty for 40,000 miles. It's known that the life of such a transmission has a normal distribution with a mean of 72,000 miles and a standard deviation of 12,000 miles. What percentage of the transmissions will fail before the end of the warranty period, and what percentage of the transmissions will be good for more than 100,000 miles? So pause this video, give this a try, and then turn it back on and we'll check your answers. Okay, let's start with a diagram. So for part A, what percentage of the transmissions will fail before the end of the warranty period? So we know that the mean is 72,000. And we have a standard deviation of 12,000 miles. And the warranty is 40,000. That's well below the mean. All right, so we're looking for all of the transmissions that will fail. So we're looking for that area under the curve. So normal CDF, lower boundary, since there is no end to this side of the curve, it's going to be negative infinity to 40,000, and with a mean of 72,000. So that's my upper boundary. 72,000 is my mean, and 12,000 is my standard deviation. When I calculate that, I get about 0.0038. That is the probability that X is less than 40,000. I'd say this company is pretty safe. All right, let's try part 2. What percentage of transmissions will be good for more than 100,000 miles? So draw another curve. Here's my 72,000. 100,000 is going to be up here somewhere. So we're looking for the probability that X is greater than 100,000. So my lower boundary this time is the 100,000. And my upper boundary is infinity, with a mean of 72,000 and a standard deviation of 12,000. And that gives me about 0.0098. Almost 1%. Okay, now we're going to find z-scores when we know the area under the curve. So let's try this. What z-score is associated with the top 15%, or we could call that the 85th percentile of a normal distribution. So the top 15%, we're going to call that z.15 of a normal distribution. Okay. We need some way to find that. We know how to find the area if we know the z-score, but we haven't had to find the z-score if we know the area. You can look it up in the table. So if I go to the table and look, all of the values in the table are the areas or the probability, and then we can find the number that goes with it. To do that, we need to look for 0.85 because the table goes from left to right, so it's going to look for it's going to show the 85th percentile, not the top 15%. So if we go in here, I'm looking for 85th percentile. That's 88, that's 86, that's 84, so somewhere between 1.0 and 1.1 is going to be the 85th percentile. So I found 85.08 and 84.85. This value is actually closer to the 85th percentile, so I'll take that one. And the z-score that goes with that is 1.04. So z equals 1.04. There's also another way to do this. If you go to your calculator and you go to distributions again, if you go to number 3, so distributions in your calculator, number 3, you'll see if you scroll down, it says inverse norm. That's the inverse of finding area. It's going to be finding the z-score if you have the area. So you do inverse norm 0.85, and you should get 1.04. All right, so let's try why don't you try finding z-score when the area under the curve is given? What z-score is associated with the bottom 10 percentile? Pause this, turn it back on when you're ready to check your answer. Well, one thing you'll want to notice is this is different than the last problem. It's the bottom 10%. So we're looking for where the area is 0.10%. If we wanted to, we could write that as z.90. And again, I could go to the table, and if you remember, the middle or the average, the z-score is 0. So I'm going to be looking for a negative value. And if I go to the table and I look for where the area is 10%, I'm going to have to go back here. So here's 0.1, here's 0.9. So somewhere in between negative 1.3 and negative 1.2 is going to be the closest value to 0.1. There's 0.193, 0.1075. All right, here we go. 0.100 looks like a 3. Boy, I need new glasses. Actually, I got new glasses and it's not that helpful. I still can't see. So z is equal to negative 1.28. Or in your calculator, you can do inverse norm. And since we're looking for the bottom 10%, it's going to be 0.10. And doing it that way, you should also get negative 1.28. All right, let's try finding the boundaries of z-scores that bound the middle 95% of data. That means that I need that means I have 0.025 here and 0.025 here, because that adds up to 5%, and in the middle I have 0.95. So I'm looking for z 0.975 and z 0.025. So inverse norm, the lower 2.5% is going to be negative 1.96, and then the upper 0.975 is going to be 1.96. Oh, look at that. That curve really is symmetrical. And if you remember from the empirical rule, it's roughly -2 and +2. But this is a little more precise. All right, so let's find z-score when the area under the curve is given. Find the value of z 0.1. So z 0.1 means the top 10%. And we really can't put that in the calculator. That's going to give us this area, where 10% is over here. We don't want that. We want the z-score, because inverse normal, unlike normal cumulative distribution function, has to go from left to right. It doesn't have a lower boundary and an upper boundary like that. So everything you put in there is left to right. So I have to put in 0.9 for the area, because it's going to give you the z-score based on whatever the area you put in. So inverse norm 0.90 is going to give me 1.28. Okay, you could put in 0.1 and you'd get negative 1.28. You just have to know that this means the top 10%. All right, so inverse norm is actually even more useful than you might think. In a large class, suppose your instructor tells you that you need to obtain a grade in the top 10% of your class to get an A on a particular exam. From past experience, she estimates the mean and the standard deviation will be 72 and 13. So that's the mean and standard deviation. What will be the minimum grade needed to obtain an A? So up till now, we've been using inverse norm to find a standard score. We can also use inverse norm to find a non-standardized score. So let's draw a picture of what we want first, of what it is we're looking for. We are looking for what value is going to give me a score in the top 10th percentile. What's the minimum grade I need to get? I also know that my mean is 72. My standard deviation is 13. So if I go into inverse norm, the syntax is I need the percentile, I need the mean, and I need the standard deviation. So be careful. The percentile is not 10%, it's the 90th percentile. The mean is 72 and the standard deviation is 13. And when I put that into the calculator, I get 88 93.66. So that's the score I would need to get to score in the top 10th percentile, or top 10%. All right, I want you to try this one using the same method. Turn the video off and turn it back on when you're ready to check your answer. Okay, so in our IQ example from the previous section, mean was 100, standard deviation was 15. Find the 33rd percentile for IQ. So percentile comes from the bottom part of the curve, left to right, not the top 10%, 33rd percent, but the 33rd percentile. So that's going to be from left to right. It's important that you learn the language. Our mean is 100 and our standard deviation is 15. So we can go into inverse normal. We're looking for the 33rd percentile with our mean and our standard deviation. And that's 93.4. So an IQ of 93.4 is in the 33rd percentile. And that's it. It's a short video tonight.